Last class, we talked about phase diagrams and slope fields, so let's bring it back to the logistic model, the density-dependent model that we started this chapter with, and produce a phase diagram and the slope field for it. So again, recall that to compute the steady states, I need to set the derivative to be 0, and in this case, what I'm going to have is bp1 minus p over k is equal to 0, which implies from the first factor that either p is 0 or from the second factor that this p will need to be k, so that this entire bracket is going to be equal to 0. These are my two states. These are my two equilibria. Now, if I open up the brackets of the logistic model, I will see that what I in fact have is a quadratic function, which means that the entire logistic model is simply a parabola with a negative coefficient in front of the p squared term. So it's a parabola looking down with 0 and k as steady states. If this is 0, and let's say somewhere over here is k, what I'm going to have for the logistic growth then is a parabola looking down like this. I can, in fact, already say a lot of information, not only about the equilibria, but also about where this peak growth occurs. Notice that this isn't the biggest value of p. Because I am sketching the derivative, this point will represent the biggest value of p prime. So at this point, which is exactly halfway in between the intercepts, so k over 2, is where the population growth is the fastest. The rate of change of population is the fastest. Now I can put on the arrows onto my horizontal axis, which will help me identify the stability of my two equilibria. Remember that if the graph is below the horizontal axis, then the arrows point to the left, and if the graph is above the horizontal axis, the arrows point to the right. Once the graph is below again, the arrows will go to the left again. This then tells me that the arrows run away from 0, which means that 0 is an unstable steady state, but arrows run toward k, which means that that will be a stable steady state. In terms of producing a slope field for the logistic model, I can already use the information from the phase diagram to realize that what I'm going to have are the two stability cases here, where 0 is in fact unstable and k is stable. If you plug in a few numbers somewhere in between 0 and k, for example, if you plug in k over 2 for p and whatnot, what we are going to see is that the solution curves will look something like this if you start with the value p naught between 0 and k, something like this if you start above, and something like this if you start below. The cases that we're going to be considering as the most realistic for the model descriptions are the cases of this curve, where the initial state resides between 0 and k. This is going to be our most standard logistic growth curve. With this in mind, what we see this curve often in are a variety of real data from the real world. For example, this is very reminiscent, all of these curves are very reminiscent of the logistic curve, but with different rates of growth. These describe Ebola cases in the 2014s and 15s in Guinea, Liberia, and Sierra Leone. These curves should also look familiar from the recent news on the coronavirus. For example, this is a log curve, which makes it easier to see the shape of the number of confirmed cases in Alberta, Canada. So again, we can see that exact same logistic curve shape. That gives us an idea that not only is this shape quite popular, let's just say, amongst the realistic models, it's also something that would be useful to, in fact, study for things like the spread of the virus or infectious disease. Now, in general, many dynamic processes involve more than one variable, And often the two variables involved are actually representing two different forms of the same thing. Before we go on to talk about specific examples, let's consider the law of mass action that some of you might have seen in chemistry courses. The rate of a reaction is directly proportional to the product of the activities or concentrations of the reactants. This is a very important word here, the product of. This is kind of like thinking of the square and how a square might grow. So for example, if I give you a little square here, and I would say that each side of it will double, what I actually get is that the entire area of the square quadruples, right? So if one side doubles and the second side doubles, the entire area is actually a product of the rates 2 time for the rate of change of one side times 2 for the rate of change of the other side. This law of mass action can be seen in a variety of examples. For example, the spread of virus or infectious disease is going to be directly proportional to the product of the number of susceptible individuals, so those not yet infected, and the number of infected individuals, those already carrying the disease. So for example, here we can say that the spread of virus is proportional, meaning I have to introduce a constant of proportionality, to the number of susceptible people, let's note that, times the number of infected individuals already. Now notice that these two things actually describe two different forms of the same thing. Both susceptible and infected are people within the population being in two different states from the point of view of the disease. This model actually extends to a number of other things. For example, spread of rumors or spread of new technologies. One of the most famous examples are how you can predict, with the same analysis we're going to do shortly on disease spread, you can actually predict things like the number of oil wells that will be opening up in the next future. So for example, in terms of the spread of rumors, we can say that the model will then be proportionality constant times h times n, where h are the number of people that heard the rumor and the n are the number of people who have not heard it yet. In the topic that is very pertinent to our current situation, we're going to consider disease dynamics and the spread of infectious diseases. How does that get modeled with differential equations, and how we can predict things like whether a disease will become a pandemic and what have we got to do in terms of vaccination strategies. This is a very general disease dynamics setup. N is going to be the number of people in the entire population, and you can define that to be a province, a country, or the entire world. And the entire population will be divided into two types of individuals: those that are already infected and those that are still susceptible. So you can think of that as you have all of your people, and they are in fact divided into two parts: the infected individuals and the susceptible. There's no one else. Once somebody recovers, they become susceptible again. So we're going to first consider a simple model with no immunity being acquired through the infected and survival technique. If everybody interacts with each other, then people get infected at the rate proportional to the product of the two types in the population, according to the law of mass action, which means that the disease spreads, so the number of infected individuals grows at the rate proportional to the number of infected individuals times the number of susceptible individuals. Now, this equation, this differential equation, isn't really the type that we ever want to see, because what we have are two variables involved throughout, and therefore we cannot really solve it, which means that what we're going to try to do is get rid of one of these. Recalling that the entire population size is n, and the entire population consists of infected and susceptible individuals, what we can do is rewrite S in terms of I and N. The number of susceptible individuals are the total number of individuals minus the infected ones. So S can be replaced with N minus I. This is already really great news. B is the proportionality constant depending on the disease and how fast it spreads. And N is the total population size, so also a constant. If I open up the brackets here, I see what I get is an equation quadratic in I, which is very reminiscent of the logistic model, which means that if I simply massage this equation and make it look different, maybe I can hope to get to the point where the entire equation looks like the logistic growth model that I already know quite a bit about. So in order for me to get to the logistic model, notice that the biggest difference is the fact that in the logistic model, I have a 1 as the first term inside the bracket, and here I have an n. So all I'm going to do is, in fact, factor out this n. So I'm going to take this out and then consider what is left in the bracket. 1 minus I over n. And this can, of course, be easily matched to my logistic growth model introduced a couple of slides earlier, where I can see that this is just a constant, and then this n is the carrying capacity. That means that the carrying capacity of the disease in this model is the entire population size. Again, that makes sense because notice that we have assumed no recovery rates. Everybody who gets infected survives, becomes susceptible once again. So eventually the entire population will get infected at some point. Because this is just a logistic growth model and we're wondering how good it is at describing actual diseases, we can of course ask for real world data. So these are some other graphs that follow the logistic curve fairly reasonably. This is the reported deaths from H1N1 in Malaysia, and you can see this exact same logistic growth graph happening here, for example, where, for example, here too, we have the number of AIDS cases in Thailand. We see the same very close to logistic curve growth, tapping out at some number. Now, some graphs will get influenced by the different things that happened in the world otherwise. So, for example, here we have the number of people living with HIV or AIDS. Notice that the number of people living have actually plateaued following the logistic growth at first. It actually tapped out at some number. So above this number, people simply did not survive HIV diseases. Now, afterwards, you notice that the graph becomes linear. So more and more people are now able to survive HIV. How come? Well, let's think about what happened somewhere in the late 90s. Vaccines and different other treatments got introduced, which allowed this plateau for the survival to actually increase. What we have to consider next to make our model a little more complex are recovery rates. What happens if individuals are recovering at a certain rate? Let's draw a rough diagram of what that might look like. So let's say I have infected individuals here. I've labeled them I before. And on the other hand, I have susceptible individuals. I've labeled that population size as before. Overall, I still have N people in the population. Now, the infected people can now recover, and the susceptible people, as they always have been able to, will become infected. The second one, the susceptible people become infected, is exactly the thing that we've already modeled. The infection rate, which was di by dt, was equal to bi times s, which was also n minus I. The thing we haven't modeled yet, and this is how we're going to make this more complex model, is the recovery rate. What is it reasonable to assume of the recovery rate? I have the number of people that are infected. How many of them are going to become susceptible again, get healthy, and therefore land in the susceptible population once again? Well, it is reasonable as a first step to assume that the number of individuals recovering is proportional to the number of individuals actually infected. So here, because it's proportional, I am going to assume that the recovery rate is some constant mu times the number of people in the infected population. This is a standard constant that gets assigned to it. It's mu, a Greek letter mu, which is just a u with a sort of long nose. Now that we've introduced this extra bit of information into our model, let's try to think about how the disease spreads according to this once again. So what I would like to know is, what is the rate of change of the infected people? How many new infections do I get? Well, it's the number of new infections minus the number of recovery rates. So, rate of new infections minus the rate of recovery. Now, both of those things I can rewrite in terms of my variables in this diagram. The rate of new infections is how fast the susceptible people become infected again. So this is BI and minus I, which is our old model. And in fact, what I have so far is our old model, the logistic growth, minus, now I'm accounting for the people that recover. So what I have now is minus mu I. Now, once again, I notice that if I open up the brackets, this term is simply linear, so I still end up with a quadratic equation in I coming from this I times negative I. So if I massage it, maybe I can make this look like the logistic growth once again. So in my next step, what I'm actually going to do, I'm going to try to combine these two terms, and I'm actually going to try to combine them by factoring out BI from both brackets. So in the first bracket, I have n minus I here. And then if I factor out BI from this term, I'm going to get minus mu over B. You can check my work here by opening up the brackets and ensuring that I have the previous line back. So now let's see what I have here. I can notice that this is a constant and this is a constant. There's no point keeping them apart. So I'm in fact going to unite this n and this mu over b into a new constant that I'm going to call, let's say, k. So my k is going to be n minus mu over b. And I'm going to rewrite this equation with my newly introduced constant. So I have that this is now k, the n and minus mu over b is what I'm going to call k now, and then I have this minus I. My I, of course, is not a constant, so I can't really change it with anything. Now, again, recall that the logistic growth has a 1 in the bracket as the first term. So in order for me to try to make it look like it, I'm going to factor out the k into the front as well. So I'm going to have bki 1 minus I over k. This is looking more and more like the logistic model growth. In fact, it looks exactly like it now. This is also just a number. I'm going to call this guy beta. Again, just following actually very standard epidemiology terminology that you will find in any epidemiology book. So if I introduce this new constant beta, which is b times k, now I can trace my k to here and my b back to the actual intrinsic rate of disease spread. What I get in the end is beta I 1 minus I over k. A logistic growth once again. So notice that, in fact, making my model more complex by introducing the idea of recovery rate did change the model and changed my constants throughout, but it didn't affect the fact that this is still a logistic growth. What it did, though, affect quite noticeably between the last case and this one is that in the last case, my carrying capacity was n, the entire population, and in this case, my carrying capacity is k, this new constant I've introduced here, which is n, the entire population, minus a number. And this number consists of a ratio of the recovery rate, sort of speed, and the speed of the intrinsic disease spread. So now my carrying capacity is most certainly less than n, and that also makes sense because now my model does in fact include the fact that people don't just get infected and get healthier or die, but rather can also recover. So this is the main difference here, is that the carrying capacity is actually different. Now, let's analyze this model because this is a more realistic scenario where people can, in fact, recover from a disease, and see if we can find the steady states for it and what would those, in fact, be. Because this is just a logistic growth, I can expect that when I factor things out, I'm going to get a quadratic equation, and I do. So this is going to be bik minus, or beta I squared, a parabola in terms of I, so a parabola looking down. If I look for steady states, I need to set my derivative to be 0, and then it's easier to look at it in the factored out form. That will give me that either the first term is 0, so I is 0. This is a simple steady state. If the number of infected individuals is 0, the number of infected individuals will always stay 0 because nobody can infect anybody else. And the second case is when this bracket is 0, so I is equal to k. So here, the trick, a very small nuance, is that we actually have to consider two cases. It's really easy to simply start drawing the case where we have I is 0 and I is equal to k, but what you have to realize is that the k does not have to be positive. This k can in fact reside on the negative side. So these are the two cases to consider, the k being positive and the k being negative. Let's go through both of them and see how that affects the situation. So if the k is negative, that means that one of my steady states is to the left of 0, so I have to make sure that I actually draw my phase diagram accordingly. So here is my phase diagram for k less than 0. And what do I have here? So this is my k, this is my 0. I know that my shape is an upside down parabola, and here is what that looks like. I can now, as before, place arrows on my horizontal axis to identify whether the found equilibria are in fact stable or unstable. So here the graph is below the x-axis, which means I'm going to point the arrow to the left. In the middle, it's above the x-axis, so the arrows go to the right, and then we go to the left again. This means that k is a unstable steady state, and 0 is a stable steady state. This is the sort of good scenario. I have that if I begin with the number of infected individuals greater than 0, the arrows will point toward 0. So the disease will in fact die out. This is what we would like to see in reality with any disease that we face. What about the other case when k is positive? So I'm going to create another phase diagram for that, keeping in mind that now my k is going to be on the right-hand side of 0, so I have to account for that. This is my case, k is positive. And what do I have here? 0 and k. I still have the parabola as my general case, but now my arrows are going to be slightly different. I notice that here the graph is below, so the arrows are to the left. In the middle, it's above, so the arrows are to the right, and then the arrows are to the left again. So what I have is that 0 is an unstable steady state, and k is a stable steady state. The steady state is now at some value k that is positive, which means that if I have a number of infected individuals above 0, the arrows will always point toward k, and this will now be my steady state. That means that this is the number of infected individuals I will always be looking at in this model. The number of infected individuals being above 0 means the disease continues to be spreading and affects that many people, and this is what we call an epidemic. There are a number of different ways to describe an epidemic as itself in terms of the constants that we've already introduced. Let's take a look at a clip from the movie called Contagion and see what are some of the useful things that one might think about.
We have 47 cases and 8 deaths as of 5 this afternoon. It's a weekend. These numbers might be low. People are staying home for a couple of days, see if they get any better.
So at this point, I think we have to believe this is respiratory. Maybe fomites, too.
What's that, fomites?
It refers to transmission from surfaces. The average person touches their face 2,000 or 3,000 times a day.
2,000 or 3,000 times a day?
3 to 5 times every waking minute. In between, we're touching doorknobs, water fountains, elevator buttons, and each other. Those things become fomites.
Is this something we want to release to the press, respiratory and fomite?
And how's the public going to react to that?
Hard to say. Plastic shark in a movie will keep people from getting in the ocean, but a warning on the side of a pack of cigarettes...
We're going to need to walk the government through this before we start to freak everybody out. I mean, we can't even tell people right now what they should be afraid of. We tried that with swine flu, and all we did was get healthy people scared. It's the biggest shopping weekend of the year.
I think we need to consider closing the schools down.
And who stays home with the kids? People that work at stores, government workers, people that work at hospitals. When will we know what this is? What causes it? What cures it? Things that keep people calm.
What we need to determine is this. For every person who gets sick, how many other people are they likely to infect? So, for seasonal flu, that's usually about 1. Smallpox, on the other hand, it's over 3. Now, before we had a vaccine, polio spread at a rate between 4 and 6. Now, we call that number the R naught. R stands for the reproductive rate of the virus.
Any ideas what that might be for this?
How fast it multiplies depends on a variety of factors. The incubation period, how long a person is contagious. Sometimes people can be contagious without even having symptoms. We need to know that too. And we need to know how big the population of people susceptible to the virus might be.
So far, that appears to be everyone with hands, a
Now
mouth, and a
that
nose.
clip and that movie entirely seems to be more relevant today than when it was actually first released. Let's try to unpack what are some of those things that the characters were talking about. In particular, what we would like to know, what is that R naught, the basic reproductive number of a disease? What we're going to start with is recalling that the number K, the carrying capacity of the disease that we introduced while we were deriving the new logistic model here, recall that we introduced this as n minus mu over b. So the total population size minus some kind of proportion between the recovery rate and the spread of the actual disease rate. So n minus mu over b. What we have in the epidemic case is when k is greater than 0. So what does that mean for how our n, mu, and b interact? That means that I must have that n minus mu over b is greater than 0, which is equivalent to saying that n is greater than mu over b, which if I multiply both sides by b and divide by m, I'm going to get nb over mu is greater than 1. This is the number that is R naught, the basic reproductive number of the disease. So as we can see here, this reproductive number R naught of the disease is a combination of the total number of people in the population, how fast the disease is spreading, and how fast the people recover. If it's above 1, then we are in the case of an epidemic. If it's below 1, then we are in the case when the disease dies out. So what we're currently trying to achieve with COVID-19 is to, in fact, bring this R naught below 1 with the various measures put in place, such as quarantine, masks usage, disinfectant, sanitizing the surfaces. This reproductive number can also be thought as the number of people, the number of new cases likely to be caused by one infected person. So if I have an infected individual, how many other people are they likely to infect? If this number is below 1, then this is when we're in the clear. The thing that R naught allows us to calculate is the vaccination strategies. So for this, let's consider what does it first of all mean to be vaccinated. When an individual is vaccinated, they are what we call removed from the susceptible population. So they will no longer at all be able to be infected with the disease. what we can introduce is a fraction of people in the population have been vaccinated and therefore have to be removed from the susceptibles or infected. If the fraction is phi, again using the standard epidemiology notation, then only the remaining 1 minus phi proportion of all of the individuals can still participate in the spread of the disease. So for example, if the fraction of vaccinated people is a quarter, then the fraction of the people that are still susceptible to the disease is 3/4. And this is where this 1 minus phi comes from. When smallpox was an endemic disease, means constantly present in the population, not necessarily as an epidemic, but just as a live version, it had the basic reproductive number of 7, which means that one infected individual could infect, on average, 7 other people with the disease. The question here is to think about what is the number of people we need to vaccinate to, in fact, eradicate this disease entirely. So let's think back to the definition of R0, which was this formula right here. So what we have is R0 is NB over mu. And we know that for smallpox, it is 7. So we would like to get this number below 1 in order to turn an endemic disease into a non-epidemic situation. If I would like to multiply this by something to get below 1, the something that I have to multiply by is, of course, 1/7. 1/7 times 7 is 1. 1/7 in itself, I would like to write it as a 1 minus something. That's 1 minus 6/7. Once you write it down this way, you can match it part by part to 1 minus phi. This is my 1, this is my phi. So this is what I have as the proportion of the population that needs to be vaccinated in order to bring down the R0 of the smallpox below 1. 6/7 of the population need to be vaccinated in order to contain smallpox. 6/7 of the population is just above 85%. So when you're reading about herd immunity, this is something to keep in mind. The herd immunity is only effective when a vast majority of population is already vaccinated. 85% of people need to be vaccinated in order for the herd immunity and the disease to not become a pandemic. Let's take a look at another example of the general setup, for example, in the context of a rumor. Let's say the rumor spread amongst the 160 students of Math 111 like an infectious disease, which is the thing that we normally actually modeled with. The other things that spread the exact same way are things like memes and news and whatnot. So what I have here is a model written in this way, which it matches my, not the logistic equation, but rather the equation for the number of new infections minus the recovery rate. Whereas to first find the basic reproductive rate of this rumor, sketch the phase line diagram and identify the stability of the steady states. So let's think about, first of all, the R0. The R0 is defined as NB over mu, where N is the total number of people in the population, B is how fast the disease spreads, and mu is the recovery rate. So I should be able to read all of those numbers straight from the model. The general model, let me write it down right underneath the given example, is from a couple of slides back, BI N minus I minus mu I. So once again, the rate of new infections minus the recovery rate. If I write it down this way, I can match 1 for 1 my terms, and in fact they line up perfectly here, to see that the B in my particular case is 0.01 and mu in this particular case is 0.5. This makes it very easy to calculate R0 quickly. The N, being the total number of people, is 160. B is 0.01, and mu is 0.5. So what I have altogether is that R naught is 3.2, which means that in terms of our rumor, we do have an epidemic on our hands. Let's sketch the phase diagram of this thing. Now, for the phase diagram, I have to identify the steady states and then their stability, which means that I need to be able to actually draw this on the graph of I versus I prime. It will be easier to see the shape of it if I simply factor everything out and then potentially combine like terms. So what I'm going to do is simplify my expression here. I'm going to open up the brackets. And in fact, I'm actually going to eventually substitute 160 for m. If I do this in a couple of steps, which I'm going to skip, let me just say ... do check my math by again opening up the brackets and combining like terms. But what you should get is 1.1 I minus 0.01 I squared. From this alone, I see that this is a logistic growth quadratic with a negative in front. So on the phase diagram, it is going to be a parabola facing down. I would like to see exactly what the intercepts are. 1.1 I, then I'm going to get 1 minus I over 110. So what I can see here is that my stable states is where this whole thing is 0, which means either the first term is 0, which will give me I equals 0, or the second bracket is 0, which will give me that I is equal to 110. Now, sketching the actual phase diagram will then mean that I have 0 as my first equilibria, 110 as my second one. And now, placing arrows on it, I see that I'm going to the left when it's below the axis, to the right when it's above, and to the left when it's below, making 0 an unstable steady state and 110 a stable steady state. So 0 is unstable, 110 is stable, which confirms the fact that this is in fact an epidemic. This means that in the long run, 110 people will be hearing the rumor. The recovery rate here is the rate of basically forgetting the rumor that you've already heard, and then you end up in the susceptible population again and are again susceptible to hearing the rumor. In the long run, 110 people here would always be aware of the rumor, and this is what defines an epidemic. Let's now think about what the solution curves might actually look like. If I have originally only 10 people that know the rumor, or if I have originally that 110 people know the rumor. If I'm asked to sketch the solution, then this is the problem for a slope field. So let's recall the general shape of the logistic growth slope field. I have that my steady states are 0 and k for whatever value of k I have here. As on the previous slide, I've discovered that my steady state or carrying capacity state here is 110. So this will be my value of k. This is when my slopes would be completely horizontal. And then my general curves, recall that for logistic growth, I have standard looking curves like this here. Above, I am going down toward the carrying capacity, and below I'm converging away from 0, which is, while being in equilibrium, is in fact an unstable steady state. So let me draw these curves here for the standard logistic curves and then see what I'm asked to sketch. The solution for I naught being 10 happens to be exactly in the region between 0 and 10. So I'm going to sketch this in red, not up to scale. Let's say 10 is here. This will follow my most general solution of the logistic growth equation. The second part is asking to sketch the solution with the initial condition 110. If I start at 110, this being in equilibrium, it means I will always stay at 110. I will never be able to leave it because it is in fact itself a steady state. So my solution curve here will simply be a horizontal line at 110. This example goes through all of the possible ways that you can ask to compute with the most general disease dynamics setup curve. So I encourage you to go through this carefully and make sure you understand every step of it.